Hi, everyone. Welcome to Juniper's Virtual Summit. Thank you for joining us. My name is Savi Venkarachalapati, and I'm part of the Juniper product management team. In this session, we want to walk you through our SONiC portfolio and various efforts to enhance the SONiC ecosystem. But before we get into it, let's look at the need for another NOS. What are some of the challenges and how are they being addressed by SONiC? Cloud infrastructures are built with best-of-breed components to provide the best services possible. These devices come with different operating systems, configuration, and management, which means additional training and slower deployment cycles. Managing disparate systems could also lead to increased failures and errors, reducing the reliability. In addition, the cloud providers operate highly available networks at a large scale, making monitoring, diagnostics, and automation table stakes. Cloud providers are seeking a homogeneous, containerized, modular operating system that could be deployed across different tiers within the data center and potentially outside of the data center. SONiC addresses all of these challenges. SONiC was initially developed by Microsoft, who open-sourced it to allow additional community development and offering flexibility to create the network solutions they need. The operating system decouples the underlying hardware and software through a switch abstraction layer to allow faster hardware innovation. The operating system itself is further disaggregated into containerized components, allowing new applications to be developed and integrated. Many vendors, including Juniper, have joined in supporting and contributing to SONiC. At Juniper, we see the need to boost SONiC performance and add new features to expand the footprint to include superspine and WAN core deployments and make it truly ubiquitous across the infrastructure. We are working on that, and we'll talk about it here as well and show you some demonstrations. Now, Lester will walk you through this.
My name is Lester Bird from Juniper Networks. The session today is Modular Chassis, MPLS, and MACSec integration on SONiC. We will be demonstrating some brand new SONiC features on Juniper's newest modular chassis, the PTX 10008. So why a modular chassis? Well, first, modular chassis exist today, so there's no reason that SONiC shouldn't have one. Some of the reasons for a modular chassis include they are widely deployed in data centers already. They have high WAN port density, a large number of ports. There's a known power consumption. There's a known rack space. One of the characteristics of a modular chassis are field replaceable units or hot swappable devices, and they support high-speed interfaces like 100G and 400G. Today, there are two options for SONiC on a modular chassis. The first is disaggregated SONiC in a chassis. In this case, the entire system is managed as a SONiC cluster. Each line card runs a SONiC instance, so there are multiple SONiC instances. There is a software switch fabric that passes Ethernet frames between line cards. If there is any through support, there's limited through support, typically line cards. Bringing down a line card means bringing down an entire SONiC node. You are bringing down one node in the cluster. At Juniper, for the PTX 10008, we chose a different approach. The system is managed as a single node in a traditional modular chassis way. As such, there's only one single SONiC instance. None of the line cards run SONiC, as they are all managed by the Juniper HAL. We have a hardware switch fabric that passes cells between line cards. We have complete through support for fans, line cards, and power supplies. Pulling out a line card means only those associated WAN ports disappear, not the entire node. We believe this to be superior because it takes advantage of the hardware switch fabric. It has simplified management, and because a single IP address is associated with the node, there are reduced routing adjacencies, leading to better scalability. Here's a diagram illustrating disaggregated SONiC in a chassis. As you can see, there are multiple SONiC instances that comprise the cluster. BGP, EV, PN, and VXLAN handle control plane distribution as well as the software fabric. Contrast that with the Juniper PTX 10008 with a single route instance, a hardware switch fabric that interconnects all the line cards. In this case, none of the line cards run SONiC. We use Juniper's Advanced Forwarding Toolkit, or AFT, to distribute routes across the line cards. AFT is part of the Juniper HAL. Field replaceable units are a key characteristic of a modular chassis. This complicates SONiC a little bit. Since SONiC typically assumes static configurations, we had to extend SONiC to handle a more dynamic behavior. With FRUs or hot swappable devices, line cards and their ports may be removed or installed after SONiC boot. They may be inserted into a different slot. Fan and power supplies may be removed without affecting system uptime. The result is a very dynamic changing system. Therefore, we had to extend show environment to reflect the current system state. The default SONiC interface naming scheme was also problematic. As we said, line cards could change slots during system uptime. Names like Ethernet 0, Ethernet 1, they fail to indicate port locations, and this is problematic for the administrator if a port has problems. Our solution is to embed slot and port numbers into a dynamically generated SONiC port name. Juniper is proud to be the first to offer MPLS on SONiC. We had to overcome a few issues. First, SONiC does not currently support OSPF and ISIS, the typical label sources for MPLS. Consequently, we must have an external SDN controller as the MPLS label source. Right now, we support basic MPLS operations, namely push, pop, and swap. To integrate MPLS into SONiC, we had to add new MPLS tables to Redis and modify the SONiC daemons to act on those tables. As the SDN controller, we use Juniper Northstar or some other suitable SDN controller. We leverage CRPD, Juniper's containerized routing protocol suite, to inject MPLS routes into the Linux kernel. And of course, we will upstream the MPLS changes to the SONiC open source community. The second new SONiC feature that we will demonstrate is MACSec with MKA. There is a new MACSec side proposal, but if you read it, you'll discover that it covers data plane operations only. We still need MKA for the control plane, and MKA must be extended with XPN to support 100G and 400G interfaces often found on a modular chassis. Like MPLS, to integrate MACSec, we had to add tables to Redis and modify the SONiC daemons accordingly. For MKA, we use open source WPA supplicant. We have added XPN, extended packet numbering, to WPA supplicant to handle high-speed interfaces. And again, we will upstream MACSec and WPA supplicant to the community. We now have a short video demonstrating MPLS, MACSec, and MKA on Juniper's PTX 10008 modular chassis. We have some exciting new innovations to talk about. Juniper has added MPLS and MACSec to SONiC. We are using Juniper's newest 400G modular chassis, the PTX 10008. Let's talk about MPLS first. This is our test topology. We're using an SDN controller to generate MPLS routes. We also have a couple of IXIA ports to generate MPLS traffic. This is the MPLS programming sequence. The SDN controller uses HTTPS to talk to an agent running on the PTX 10008. The agent uses the Juniper Extension Toolkit to talk to CRPD, Juniper's advanced routing stack. CRPD adds the routes to the Linux kernel. It publishes to Redis, where syncd picks up the publication. syncd calls Psi to program the PFE's fib. Let's go to the console and execute some commands. From this screen, we see that the agent has received 140 MPLS routes from the controller, and CRPD has programmed all of them. We see the push, pop, and swap routes. Using the standard IP route command, we can verify that CRPD has installed the MPLS routes into the Linux kernel. To make MPLS work with SONiC, we had to add a few Redis tables. We show them here briefly. As might be expected, there's also MPLS information in the ASIC DB. We now verify that the routes have been programmed from SONiC to the PFE fib. Lastly, we confirm that the PTX 10008 is doing the MPLS work like we expect. We bring up Wireshark and look at the packet decode. Here we see a MPLS packet. This is an MPLS swap. That's MPLS in a nutshell. Let's take a look at MACSec now. This is our test topology. But before I get too far, I want to tell you something that's exceptionally noteworthy. The PTX 10008 can do 400G line rate MACSec. Isn't that awesome? I'm working on a video for it, so keep a lookout. For now, we'll show you how we integrated MACSec into SONiC using a much simpler topology. Let's type some commands. First, note that we've added a new MACSec stanza to configdb.json. We've also added a new MKA Docker container. The main process in this Docker container is open source WPA supplicant. We've added XPN to WPA supplicant to handle 100G and 400G interfaces. WPA CLI allows you to look at current MACSec information. Finally, we ping between the PTX 10008 and the Linux server, the MACSec Pure. As you see, ping is successful. An interesting experiment happens when we kill WPA supplicant on one side of the MACSec tunnel, in this case the Pure. When we kill WPA supplicant, ping stops. When we restart WPA supplicant, ping resumes as expected. We can also look at MACSec activity by examining the normal SONiC logs. As I mentioned, we plan to give back many of these changes to the SONiC community. These include MPLS, MACSec, MKA with XPN, through insertion and removal, dynamic interface naming, and corresponding Ansible test scripts to test this new functionality. All these new features will be available eventually in SONiC open source release code. We are currently formalizing upstream plans.
Thank you for joining us. And if you'd like to learn more information about the SONiC features and the enhancements, please visit our website. Thank you.